Hello everyone, welcome back to Math and Chemistry channel. Today I'm going to record a lecture on approximate methods in quantum chemistry. Here I'm going to discuss the application of variation method or variation principle to helium atom. So here I have written few points based on variation method or variation principle. So variation method is a approximate mathematical approach which is used to solve the complex problems, or we can say which is used to find the approximate energy values of the complex system comparable to the true value. True value is denoted by E naught. Now, what is the basic principle of variation method? In variation method, first we guess the trial wave function for the system, and this trial wave function, it contains some variational parameters. Then these variational parameters are fixed to minimize the energy for the chosen trial wave function. And variation method, it provides the energy of the system which is always be upper bound to the true value. Means in the variation method, first we choose the trial wave function which contains some variational parameters. Then what we are discussing the application of variation method. So which application we are going to discuss here? We will find out the ground state energy of helium atom. Ground state energy of helium atom. So now to find the ground state energy of helium atom or any other atom, what we require? We require Hamiltonian and we require wave function. So we require these two parameters. First is the Hamiltonian operator and second is the wave function. Right? But for the complex system, wave function is not known to us. For the complex system, wave function is not known to us. So here what we do, we select or we guess some trial wave function. And to that trial wave function, we apply the Hamiltonian like this. So when we apply the Hamiltonian, it provides us the energy value. Right? So here energy is the eigen energy value. So here what we do, we multiply on both sides by psi star. And we do the integration on both sides. Because E is the eigenvalue or constant, so we can find this value or we can write it as integration of psi star h psi upon psi star psi d2. This is the volume element. Now, if your wave function is normalized, if the wave function is normalized, then this denominator factor, it will be 1. Because for normalization, we know the condition, the product of psi, the integration of product of psi or psi square, it is equal to 1 if the function is normalized. Right? So to find the ground state energy of the helium atom, we require Hamiltonian, we require wave function. Then we apply this Hamiltonian on this wave function and we get some value. Now this value we are getting from the trial wave function. This is not the exact wave function. This is the trial wave function. Okay. And this value we are getting the approximate value. Now variation principle, as I have written over here, it always provide the energy of the system which is upper bound to the true value. Means the value that we are getting by using the trial wave function, it will always be greater than or equal to true value. What is E naught? E naught is the true value. This is the experimental value of energy for the ground state for helium atom. Okay, so why we are using this approximate method? I hope this is already clear to you, because we know helium atom is multi-electron system. So for multi-electron system, we cannot apply the Schrodinger wave equation. Schrodinger wave equation is applicable for hydrogen atom, for particle in one-dimensional box, two-dimensional box, three-dimensional box, and for rigid rotor, for simple harmonic oscillator. For such kind of systems, we can solve by using Schrodinger wave. We can find the solution by using Schrodinger wave equation. But for the systems which are multi-electron systems in which the inter-electronic repulsion arises, we cannot use Schrodinger wave equation. For those systems, we apply approximate methods. So variation method is one of the approximate method. So in this method, first we will try to find the trial wave function, then we will find the Hamiltonian operator, and then we apply that Hamiltonian on the wave function to find the energy. So all these steps we will follow to find out the energy of the helium atom. So let's get started with the derivation. So as I said, we require Hamiltonian and wave function for helium atom. So let's first discuss about the helium atom. We know helium atom is two electron system. It is, sorry. So helium atom is two electron system, right? And having one nucleus. So we can represent helium atom like this. So here I'm representing plus by the nucleus. And here we have two electrons, electron 1 and electron 2. Let's suppose the distance of electron 1 from the nucleus is R1 and the distance of the second electron from the nucleus is R2. And the inter-electronic distance between electron 1 and electron 2, it is R12. Right? So here you can see in this system, three interactions are taking place. So first interaction is between electron 1 and nucleus. Second interaction is between electron 2 and nucleus. Third interaction is between electron 1 and electron 2. This is known as inter-electronic interaction. Inter-electronic interaction, or we can write repulsion between the electrons. So these three interactions constitute your potential energy. These three interactions are responsible for the potential energy, right? So here we will write the potential energy of the system. We know the formula for potential energy. It is equal or proportional to Q1 into Q2 by R. Q1 and Q2 represent the charge and R represent the distance of the electron from the nucleus. So let's suppose Q1 represent the charge on the nucleus, Q2 represent charge on electron. So first potential energy term I'm going to write for the first interaction that is taking place between electron 1 and the nucleus. So Q1 means charge on the nucleus, which is Z, and the charge on the electron is minus E. So I'm writing minus ZE upon distance is R12. Similarly, we'll write the expression for potential energy for the second interaction. Distance is R1. And here I'll write R2. Then third is the interaction between the two electrons. We know the charge on electron is minus E. So potential energy will be E square upon R12. So this is the expression for potential energy. Okay. So as I said earlier that to find the energy of the ground state energy of the helium atom, we require Hamiltonian, right? So we need to write the Hamiltonian. We know Hamiltonian is then an energy operator which consists of kinetic energy and potential energy. So potential energy term we know, okay? So now we will write the kinetic energy for the helium atom. So as we know, helium atom consists of two electrons, right? If we have one electron, then how we write the Hamiltonian? We write Hamiltonian equals to minus h cross square upon 2m del 1 square. Okay. For the if we have only one electron, what is del? Del is the Laplacian operator, which is equal to curl square upon curl x square plus curl square upon curl y square plus curl square upon curl z square. But we know our helium atom consists of two electrons, so we will write two Laplacian operators. So for the helium atom, the Laplacian operator or the kinetic energy, here I am writing the kinetic energy. This is also kinetic energy. So kinetic energy equals to, for two electron, minus h cross square upon 2m del 1 square for the first electron and del 2 square for the second electron. So this is the expression for kinetic energy. Now we will write this kinetic energy and potential energy here in this expression to get the Hamiltonian. So Hamiltonian is an operator. So we write the operator by putting cap on it. So here we will write the expression for kinetic energy, which is equal to minus h cut square upon 2m del 1 square plus del 2 square. Then we'll write the potential energy term minus Ze upon R1 minus Ze upon R2 plus E square by R12. This is R12. We can mark this equation 1. Now we will write this Hamiltonian operator expression in atomic units. You know, in atomic units, H cross mass charge on the electron, it is approximately equals to 1. So in the Hamiltonian, in place of H, M and E, we will write 1. Also, we know Z for helium, it is 2. So in place of Z, we will write 2. So H will be equal to minus 1 by 2 del 1 square minus 1 by 2 del 2 square minus 2 by R1 minus 2 by R2 plus 1 by R12. So we will write this equation second. So here we have found the expression for Hamiltonian. Now we are left to find the wave function for helium atom so that we can apply this Hamiltonian over that wave function to get the energy, right? So how to find this wave function? We don't know anything about the wave function for helium atom. So how to find the wave function? Let's see. Students, have patience because this derivation is going to be lengthy. Okay. So here we know that helium atom is two electron system whose electronic configuration can be written as 1s2. 1s2, I can write it as 1s1, 1s1. So see, this 1s1 configuration represent the configuration of hydrogen atom. This also represent the configuration of hydrogen atom. Let's suppose this is for first hydrogen, this is for second hydrogen. So you can see that this helium atom is equivalent to two hydrogen systems. Okay. So we can consider or we can assume that helium atom is equivalent to 1 electron hydrogen atom. Okay, so from here you can see this helium atom is it is equivalent to 2 hydrogen system, which is 1 electron system. So that means we can use the wave function of hydrogen atom to define the wave function of helium atom. Okay, how? Let's see. We know. Okay, so let's write one line over here. So to define the wave function, of helium atom, we will use the normalized wave function of hydrogen atom. Okay, so let's suppose this psi R1, R2 represent the wave function for helium atom, where R1 represent distance of first electron from the nucleus, R2 represent distance of second electron from the nucleus, and it is equal to the product of the wave function of first hydrogen atom, in which electron is present at distance R1, into again the same wave function but for second hydrogen, in which electron is present at distance R2. Okay, we know the wave function for hydrogen atom is normalized wave function, and we know the expression also. So the expression of the wave function for hydrogen atom is z cube upon pi a naught cube whole under root e raised to power minus z r1 by a naught. Right? And for second hydrogen, the wave function will remain same, the expression will remain same. Just there is one difference. In place of R1, we will write R2. Okay. So students, like we have written the Hamiltonian in atomic units, we will write these wave function also in atomic units. So how to write the wave function in the atomic units? We will, wherever we have written a naught, we will put it equal to 1. So my wave function will be z cube upon pi 1 by 2. It's 1 by 2. E raised to power minus z r1. Similarly, this one will be same. We will not write a naught. A naught equals to 1 according to atomic units. Okay. Now we will use these wave functions in this equation. So the wave function for helium atom will be equal to the product of these two, z cube by pi 1 by 2 e raised to power minus z r1 multiply by z cube by pi 1 by 2 e raised to power minus z r2. Now we will solve it. We will combine the similar terms. Now z cube by pi is 2 times, so that will remove the under root. And the exponential term powers will be added. Here z is common, so I'll write r1 plus r2 in the bracket. So this is the wave function Sorry, this is the wave function for helium for 2 electrons. Okay. So you can mark this equation third. Okay. So students, now we know the wave functions. Okay. And we know the Hamiltonian. So third thing that we will find is energy. Now energy is left to find out. Okay. We know to find energy, we need Hamiltonian and wave function that we know. And now let's find the energy. Let's see the formula to find the energy of the system. We are finding the energy of the system by using approximate wave function. So this is the approximate wave function that we have derived from by using the wave function of hydrogen atom. Okay. So let's see how to find the energy. So this is the expectation value of energy, which is equal to integration. I am writing double integration here because my helium atom is consist of 2 electrons. Psi star h cap psi d tau 1 d tau 2 upon psi star psi d tau 1 d tau 2. Okay, so psi star represent the complex conjugate. It represent complex conjugate of the wave function. You know, my wave function is real. You can see in the third equation, wave function is real, does not contain any imaginary part. So the complex conjugate of the wave function will be equal to psi. Also, this wave function is normalized. Okay, this is normalized. If it is normalized, that means this factor is equal to 1. Means the denominator factor is equal to, this is equal to 1. So my expectation value expression now becomes psi star h cross psi d tau 1 d tau 2. Okay. So to find the expectation value of energy, we require wave function, we require Hamiltonian. That is already known to us. Right. So now here in place of h, in place of Hamiltonian, I will write the expression. Now the derivation is going to quite lengthy, but it is easy. So here I will write the expression of Hamiltonian. So Hamiltonian was equal to minus 1 by 2 del 1 square minus 1 by 2 del 2 square minus 2 by R1 minus 2 by R2 plus 1 by R12. So this is the Hamiltonian operator. Rest of the term I will write as it is. Okay. Now I will write, again I will solve this. Okay. I will separate the integration sign for every term. So in the bracket we have total 5 terms, 1, 2, 3, 4 and 5. Okay, so I will write separately the integration. So this is psi star. This is 1 by 2 del 1 square. So I'm writing 1 by 2 out of the integration sign. Here I'm writing del 1 square. Here we have psi. I'm just multiplying the wave function inside the bracket. D tau 1, D tau 2. Similarly, write the for second term. Minus 1 by 2 integration psi star del 2 square psi d tau 1 d tau 2. Now write for the third. Again we have psi star, we have this term and we have psi. Okay. 2 I will write outside. This is psi star 1 by R1 psi d tau 1 d tau 2. Again we will write for the fourth expression, integration, double integration to psi star 1 by R2 psi d2 1, d2 2. Last term is left. Psi star 1 by r12 psi d2 1, d2 2. Now you can see, students, we have total five integrations. This is the first one, second, third, fourth, and fifth. Now we will solve these integrations one by one. After solving these integrations, we will substitute the values in this expression to get the E value, right? So you can mark this equation number 4. Okay, let's see the previous equation. I have number 3. Yes, this is the fourth equation. Now to solve this equation, to solve the first integral, we require del 1 expression, del 2 expression. So del 1 and del 2, these are Laplacian operators, right? But here we cannot use the Laplacian operator in terms of Cartesian coordinates. So here we will use Laplacian operator in the polar coordinates. So the expression I'm writing here, del 1 square, I'm writing for del square. Del square equals to 1 by r square, curl by curl r square, curl by curl r, plus 1 by r square sine theta, curl by curl theta, curl by curl theta. Inside the bracket, we have sine theta, curl by curl theta, plus 1 by r square sine square theta, curl square over curl phi square. So this is the expression of del square. Okay. So in this expression, you can see we have three differentials. First is with respect to distance r, second is with respect to theta, and third is with respect to phi. Okay, and we here with the del 1 square we have psi. That means here we will apply this del square on phi, on the psi wave function, right? So here psi will come. So student, you can see in the wave function of helium atom, I'll show you the expression here. So in this expression, the third equation, you can see there is no theta and there is no phi part, right? If there is no theta and no phi part, that means the differentiation of the wave function with respect to theta and with respect to phi will be 0. Okay. So here we will write. So here we will write one line that the wave function of helium atom, the wave function of helium atom does not contain theta and phi. So the differentiation factors curl theta, curl psi over curl theta, and curl psi over curl phi will vanish. Okay. So that means we will be left with only one term. So in the del square expression, this value and this value, these two will be 0. So del 1 square for the first electron will be equal to r1 square curl by curl r1, r1 square curl by curl r1, right? Similarly, del 2 square will be equal to 1 by r2 square curl by curl r2, R2 square curl by curl R2. Okay, so this is the del 1 for the first electron, means for electron 1, Laplacian operator for electron 1, and this is the Laplacian operator for electron 2. Now we will solve the first integral and second integral by using these del 1 square expression and del 2 square expression. Okay, one thing more, you can see the expressions for integration 1 and integration 2. Expression is the same, just difference is here we have del 1. Here we have del 1. Okay, and here we have del 2. This is the only difference. But when you will solve the integration 1, you will, and when you solve the integration 2, you will get the same result. So there is no need to solve integration 2. We will solve only in part 1. Okay, because the result of part 1 is similar to part 2. Similarly, the integral third and integral fourth, both are same. The difference is here we have 1 upon R1, here we have 1 upon R2. So the result of third and fourth will be same. And the result of fifth will be different. Okay, means result of first and second integral is same. Result of third and fourth integral also same. And result of fifth integral is different. Okay. So students, here I am ending the first part of this lecture. I will continue this derivation in the second part. Thank you so much for watching the first part of this video.